Quantum computing is moving faster than ever, and 2025 saw breakthroughs that bring us closer to the era of truly practical quantum machines. From cloud providers building their own chips to new ways of simulating molecules and even testing theories about the universe itself, quantum computing is stepping out of labs and into real-world applications. Today, we're breaking down the top 11 quantum computing discoveries of 2025 and why they matter for science, technology, and the future of computing. Number 11. AWS launches its first proprietary quantum chip. When most people think of Amazon, they think of fast shipping or cloud services. But in 2025, AWS quietly took a huge step into quantum hardware. They introduced a superconducting quantum chip called Ocelot. Until now, Amazon's quantum platform, Bracket, allowed researchers to run experiments on hardware from companies like IonQ, Rigetti, and Quera. But now, AWS has its own processor inside their labs. It's still early. Nobody claims Ocelot is breaking speed records or has the highest qubit counts, but what matters is that a major cloud provider is building physical quantum hardware, not just renting access. This shows there's real-world demand for quantum services. Banks, biotech firms, and research labs are already using AWS for encryption tests and molecular simulations. With Ocelot, quantum computing starts to feel less like a lab curiosity and more like a cloud service that scientists and enterprises can access remotely. Number 10. Practical quantum algorithms using circuit knitting. Most quantum chips today are relatively small, usually between 50 and 100 qubits. That's not enough for massive circuits used in advanced chemistry or optimization problems. Instead of waiting for 1,000-qubit machines, researchers turned to circuit knitting. The idea is simple. Take one big quantum problem, split it into smaller pieces, run them on multiple chips, and let classical computers stitch the results together. By 2025, circuit knitting stopped being theoretical and became a real tool. Platforms like Qt, Cirq, and AWS Bracket now support it. Early demonstrations showed molecular energy calculations that were previously too large for a single chip could run across multiple devices. It's slower than a single large processor, but it works now. This allows researchers to test practical quantum algorithms today rather than waiting for larger processors to arrive. Number 9. Google's Willow stress-tested to new stability thresholds. Quantum chips are incredibly sensitive. They need ultra-cold refrigerators, vibrations must be minimized, and even tiny temperature changes can break computations. In 2025, Google pushed its 105-qubit Willow processor through extended stress tests. The chip held coherence during thousands of operations and repeated experiments. Stability might not be flashy like a speed record, but it's crucial. Early quantum processors often lost accuracy under heavy workloads. With Willow, researchers could run quantum simulations for physics experiments and test quantum machine learning models without the processor failing mid-run. This milestone proves that superconducting qubits can handle real, repeated work, an essential step towards scalable quantum hardware. Number 8. IBM's Quantum System 2, the first modular quantum data center. Most quantum computers today are standalone lab machines. IBM took a different approach and built Quantum System 2, a modular setup combining multiple cryogenic refrigerators, racks for quantum chips, classical control servers, and networking, all in one platform. The goal? Scale quantum computing like classical supercomputers. Connect multiple processors rather than rely on one giant chip. By early 2025, IBM began linking Heron processors inside the system, letting chips share control electronics and runtime software. It's not a giant quantum supercomputer yet, But the design is practical, scalable, and closer to a production-ready platform. This is one of the first attempts to turn quantum hardware into a cluster-like system, rather than a single experimental device. Number 7. IBM's Heron processor crushes crosstalk issues. Noise is the #1 enemy of quantum hardware. Even if a chip has enough qubits, interference between them, called crosstalk, can ruin calculations. IBM's Heron processor, with 133 superconducting qubits, solved this problem using tunable couplers. These couplers control which qubits communicate and when, dramatically reducing interference. Early testing showed Heron delivers 3 to 5 times better performance than previous processors due to cleaner signals. Reduced crosstalk allows more complex algorithms with fewer errors. Reliable qubits are just as important as qubit count because they let researchers run deeper circuits with more accurate results. Heron also integrates into modular systems like Quantum System 2, paving the way for scalable, stable platforms. Number 6. Microsoft's Majorana 1 topological core. Instead of building bigger chips, Microsoft is experimenting with topological qubits, which store quantum information in exotic states that are naturally more stable. Their Majorana 1 chip is a small prototype, but the approach is revolutionary. Topological qubits resist certain types of noise, reducing the need for massive error correction. Traditional superconducting or trapped ion systems need thousands of physical qubits for just a handful of logical qubits. Microsoft's method could dramatically shrink that gap. Majorana 1 won't replace existing quantum platforms immediately, but it demonstrates a path to longer-lasting, more fault-tolerant qubits, a critical challenge in quantum computing. Number 5. Quantum molecular geometry with nuclear spin molecular ruler. Quantum computers aren't just about speed. They can measure things classical methods cannot. In 2025, researchers used quantum many-body nuclear spin echoes to act like a molecular ruler, mapping the geometry of molecules with incredible precision. Traditional methods like spectroscopy or electron microscopy struggle with tiny or overlapping signals. Quantum spin echoes can probe molecular interactions in ways classical sensors cannot. This breakthrough has practical implications. Better molecular geometry could accelerate drug discovery, materials science, and chemical engineering. Quantum computing here is acting as a scientific instrument, not just a computational tool. Number 4. D-Wave simulates false vacuum decay. Quantum computing is also exploring fundamental physics. In 2025, D-Wave researchers simulated false vacuum decay, a theoretical event where a stable region of space might jump to a lower energy state. Classical computers struggle with these calculations due to enormous complexity and memory requirements. The D-Wave system modeled the energy landscape in a way classical machines cannot reproduce at scale. While still theoretical, this shows how quantum devices can tackle problems in physics that were previously beyond reach. Different quantum technologies, gate-based and annealing-based, may specialize in different scientific challenges. Number 3. IBM's Condor breaks the 1,000-qubit barrier. IBM crossed a symbolic milestone in 2025 with Condor, a superconducting processor with 1,121 qubits. This is the largest publicly reported quantum processor to date. More qubits alone don't guarantee performance. Connectivity, stability, and noise are equally critical. Condor fits into IBM's modular roadmap, meaning multiple chips can work together in systems like Quantum System 2. It's a major leap in engineering, signaling that large-scale, superconducting architectures are now feasible, not just theoretical. This milestone mirrors the early days of classical supercomputers, tiny prototypes growing into massive, complex machines. Number 2. Certified true randomness from a 56-qubit quantum computer. Cryptography depends on unpredictable numbers. Classical computers generate pseudo-random numbers that can be reverse engineered. In 2025, a 56-qubit quantum processor produced mathematically certified randomness. This breakthrough matters because it ensures long-term secure encryption. Quantum randomness is fundamentally unpredictable, and now researchers can mathematically prove it. Banks, secure messaging platforms, and government agencies are already exploring this technology to safeguard data in a post-quantum world. It's a small experiment with enormous implications for cybersecurity. Number 1. Google proves real quantum advantage in hardware. For years, quantum advantage was mostly theoretical. Could a quantum computer solve a practical problem faster than the best classical supercomputers? In 2025, Google demonstrated it with quantum echoes on their Willow processor. The processor solved a physics-grade problem 13,000 times faster than classical simulations. Unlike previous claims, this was a structured algorithm applied to a real scientific modeling task, not random circuit sampling. It ran on actual hardware, proving that quantum machines can outperform classical systems in certain tasks. While it doesn't mean quantum computers replace classical machines, it's a definitive step into the era of practical quantum advantage. The takeaway: 2025 wasn't just about incremental improvements, it was about real milestones in hardware, algorithms, and applications. Cloud providers building chips, modular quantum data centers, topological qubits, certified randomness, and real quantum advantage all point toward a future where quantum computing is practical, scalable, and ready for real-world impact. If you made it this far, let us know what you think in the comment section below. Are you excited about the practical impact of quantum computing? Which breakthrough do you think will change the world first? For more fascinating topics, make sure to check out the recommended video you see on your screen right now. Thanks for watching.